It's called the Joule-Thomson effect, and chances are you've experienced it 1,000 times without even knowing its name. Seriously, just think about it for a second. You press the nozzle on a can of deodorant, or maybe some compressed air for your keyboard, and bam, the can gets freezing. It's such a common, everyday thing, but what is actually going on inside to make it get so cold so fast? So let's call this the cold can puzzle. We are absolutely going to solve it. And as we do, we're going to uncover a fundamental principle of physics that powers everything from the refrigerator in your kitchen to rockets launching into space. The whole secret, the key to this entire puzzle, is all about gas expansion. See, inside that can, a gas is crammed into a really small space under super high pressure. The moment you press that nozzle, you're giving it an escape route. It rushes out into the open air where there's way, way less pressure. And that sudden, rapid change, well, that's where the magic happens. Okay, so this whole phenomenon has an official name, and it's the star of our show today, the Joule-Thomson effect. So what is it? The Joule-Thomson effect is basically the temperature change a gas goes through when it expands from a high-pressure zone to a low-pressure one. And the important part here is that no heat is being added or taken away from the outside. The temperature change comes completely from within the gas itself. And the process itself is surprisingly simple when you break it down. Step 1, you've got a gas packed in under high pressure. Step 2, you let it expand really fast through a tiny opening, like a nozzle. Step 3, it's now in a big, low-pressure area. And the result, its temperature changes. For most gases in our everyday lives, that change is a drop. It gets colder. But, and this is a big but, here's where the story takes a really fascinating twist. Because it turns out that this expansion doesn't always mean things get colder. It all comes down to something called the inversion point. So this leads us to the big question, right? Does a gas expanding always make it cool down? You'd think so, but the answer is, surprisingly, no. It completely depends on the starting temperature of the gas before it even begins to expand. And this is where we need to talk about the inversion temperature. You can think of it like a critical switch for each gas. If the gas is below its special inversion temperature when it expands, it cools down. But, and here's the crazy part, if that same gas starts out above its inversion temperature, the exact opposite happens. It actually heats up. This is the big aha moment right here. Below that critical temperature, expansion causes cooling. Above it, that very same expansion causes heating. We're talking two completely opposite outcomes from the exact same process. The only thing that changed was the starting temperature. Wild, right? So what on earth is causing this bizarre behavior? Well, the answer gets into the difference between the gases that exist in our real world and a kind of simplified theoretical model that scientists call an ideal gas. You see, in physics, to make the math easier, scientists often imagine a perfect or ideal gas. In this imaginary gas, the molecules are just points. They don't take up space, and they don't interact with each other at all. And for this perfect, ideal gas, the Joule-Thomson effect is zero. Nothing happens. No temperature change. This whole cooling and heating thing only happens with real gases, the kind in our spray can. Why? Because real gas molecules actually have tiny little forces of attraction between them. So when the gas expands and the molecules fly apart, they have to use energy. They have to do work to overcome that attraction. And where do they get that energy? They take it from their own motion. Less motion means less kinetic energy, which we feel as, you guessed it, cold. And this explains some weird exceptions, like hydrogen and helium. Look at their inversion temperatures. For hydrogen, it's minus 73 degrees Celsius. For helium, it's a mind-boggling minus 249 Celsius. So at normal room temperature, both of them are already way above their inversion points. So if you let them expand, they don't get colder. They actually get a little bit warmer. All right, so now that we've got the science down, let's talk about the really cool part, how we put this effect to work. Because this isn't just some neat party trick with a can. It's a technology that literally built the modern world. It is not an exaggeration to say that this simple ability, forcing a gas to cool itself down just by letting it expand, is one of the most important industrial processes we have ever developed. It's a foundational piece of technology that makes so much of our life possible. And the applications are just everywhere. Your refrigerator, your air conditioner, they run on this exact principle. It's the core idea behind cryogenics, the science of super cold. It's how we make liquid nitrogen for science and medicine, and liquid oxygen and argon for all sorts of industrial uses. It's all thanks to the Joule-Thomson effect. And if you want to see just how powerful this is, look no further than helium. Its inversion temperature is 24 Kelvin. That is just a few degrees above absolute zero, the coldest temperature that's theoretically possible. That means to turn helium into a liquid using this effect, you first have to pre-cool it below that impossibly cold temperature. The fact that we can do that is just incredible. So there you have it. We went from a simple cold spray can all the way to the frontiers of cryogenics and space exploration. The Joule-Thomson effect is this powerful, hitting force that's constantly shaping our world. And it leaves us with one last really fascinating question to think about. As we get better and better at creating extreme cold, what future breakthroughs in medicine, computing, or energy is it going to unlock next?